Okay, so so there we have it. That's the so knowing the Legendre polynomials, okay, and these are defined with respect to a variable x. In our case, x is equal to cosine theta. Okay, so that tells us then how to calculate the associated Legendre functions. Okay, which depend on both L and M. Okay, so there's a different function for each value of L and each value of M, and we see that we have quantization. L is now another quantization number, quantum number. It takes on discrete values 0, 1, 2, 3. Okay, so L is greater than or equal to 0 and is an integer. Okay, and so the polar equation gives us another quantum number. So now we have the angular equation, which involves theta and phi, gave us two new quantum numbers. Okay, m sub L and L. Okay, and we'll see in a second what we've seen. What m sub L quantizes. It quantizes the z component of the angular momentum. We'll see in a minute what L quantizes. Okay, but the first thing to notice is that if we take the derivative of these Legendre, so recall here, if we look here, the associated Legendre function involves a derivative to the mth derivative of the Legendre polynomial. Okay, so if we look at what P1 is, okay, so when L is equal to 1, if we take the derivative of that, then we just get 1, so that's equal to P0. If we take the second derivative of P1, then we get 0. Similarly, if we start with P2, if we take the derivative, one derivative, we get 3x. If we take the second derivative, we get 3. If we take the third derivative, we get 0. And so what we see is that if we go to up to if this order of derivative is equal to 0, that would imply that the associated Legendre function would be equal to 0 because it involves that derivative. And that would mean that our polar function phi would be equal to 0, and that can't be. That's a trivial solution. That means that the wave function doesn't exist, that the polar wave function doesn't exist, and we know that can't be. That's not physical because the electron, for example, in a hydrogen atom, has to have some probability distribution. Okay, and so what that means is that the absolute value of m sub L has to be less than or equal to L, so that you only take only can take the derivative up to the order of L. Okay, so for example, for dp2, for P2, we can only take the second derivative. The third derivative is too much, and so that again that puts a limit on the values of m sub L, which we can have for any given L. Okay, and so again, ml can take on the values from minus L in integer steps up to L. Okay, and so there are 2L plus 1 values of m sub L. So whatever the number L is, we'll see what that means, then we have 2L plus 1 possible values of m sub L ranging from minus L to L in integer steps. Okay. So A here, A is just the typical normalization constant, and basically we're sucking in we're folding in the normalization constant from both the phi and theta directions into this constant A, and so we want to integrate phi from 0 to 2 pi, integrate theta from 0 to pi, and now we combine big theta and big phi into y again, and we square that, the absolute value squared. Okay, and then we take the when we're doing integrations in the angular directions in polar coordinates, we have to multiply by sine theta d theta d phi, and that whole derivative, that whole integral has to be equal to 1. And I'm not going to go through again. That's something else I'm not going to go through. But when you do that, you find that the normalization constant, and so now we can basically write the full form of these YLMs. Okay, these the angular part of the wave function YLM, and I've written the first few here.